I see a linear kernel here. This kernel models relationships between data points using a simple straight line. It doesn't have a length scale like the RBF kernel. Instead, it directly captures linear trends in your data. The plus sign represents adding kernels. We're combining the strengths of the RBF and linear kernels. The RBF kernel, also known as the radial basis function kernel or squared exponential kernel, is what I'd use to model smooth, curvy relationships. It uses a length scale parameter that dictates how wiggly or smooth the resulting curve is. A smaller length scale means more wiggles. This is the result of adding the RBF and linear kernels. The combined kernel's strength lies in its ability to capture both the smooth, nonlinear aspects from the RBF and the linear trends from the linear kernel simultaneously. This makes it really versatile. I'll explain the radial basis function kernel. It's a popular kernel in machine learning because it models smooth, curvy relationships between data points. A key part is its length scale parameter, which controls how wiggly the resulting curve is. A smaller length scale means a more wiggly, less smooth curve, while a larger one gives you a smoother curve. Think of it like drawing a curve with a thick or thin marker. Pretty cool, right? This parameter, often represented by the Greek letter lambda, directly influences the smoothness of the RBF kernel. A smaller lambda value results in a more flexible, wiggly function, while a larger lambda leads to a smoother function. I find visualizing it as the wiggliness control very helpful. The linear kernel is much simpler. It models relationships as straight lines. It directly relates the input variables to the output, without any curvature or nonlinearity. This is great for datasets that have a very clear linear trend. This is the result of adding the RBF and linear kernels. The magic here is that it combines the strengths of both. It can capture both smooth curves from RBF and straight lines from the linear kernel. This makes it very flexible and able to fit a wide range of data patterns. It's like getting the best of both worlds. This simply means how we put the RBF and linear kernels together. We're literally adding them. In math terms, imagine it as taking the output of the RBF kernel and adding it to the output of the linear kernel. This summation creates a new, more expressive kernel. This allows the model to fit relationships that are partly linear and partly smooth and curved. This symbol represents the addition of the two kernels. The RBF kernel's output and the linear kernel's output are directly summed to produce the output of the combined kernel. It's simple arithmetic, but with powerful effects in the context of kernel methods. The combined kernel inherits the best aspects of both its components: smoothness from the RBF kernel and linear trends from the linear kernel. This makes it very powerful and versatile for modeling complex relationships in data. This is why we love it so much. I'm using Gaussian process regression, a powerful machine learning technique, and I'm combining two different kernels, RBF and linear. Think of kernels as building blocks that help the model understand the data's underlying relationships. The question tests my understanding of how combining these kernels affects the model's behavior and predictions. This statement is correct. Yay! Because I'm adding an RBF kernel, which creates smooth curves, and a linear kernel, which creates straight lines, my combined kernel can capture both smooth, curvy relationships and linear trends in the data. It's like giving my model the best of both worlds. This statement is incorrect. I won't simply average the length scales. Instead, the model will optimize each kernel's hyperparameters, like the length scale of the RBF, individually, finding the best values during the learning process. Think of it like finding the perfect balance between two ingredients in a recipe. I don't just average the amounts. Nope, this statement is also wrong. Oops. I don't add the hyperparameters directly. The optimization process finds the best values for each kernel's hyperparameters separately, not by adding them together. This is false. While a combined kernel often performs better by capturing a broader range of data patterns, there's no guarantee it will always outperform the individual kernels. The best choice depends on the data itself. I'm using Sklearn's Gaussian process regression, a powerful tool for predicting values based on data. I'm combining two types of kernels, the radial basis function, RBF, and the linear kernel, to build a more flexible model. This combination will let me capture both smooth curves from RBF, and linear trends, from linear. This is the quiz question. I need to carefully consider how the properties of each kernel combine. This is a correct statement. The combined kernel's power comes from taking the best of both worlds. The RBF kernel gives me smooth curves. The linear kernel adds the ability to model straight lines. The combined kernel can handle more complex data patterns. This is incorrect. While often a combination improves performance, there's no guarantee. The best performing kernel depends on the specifics of the dataset. This is wrong. I don't simply add the hyperparameters together. Instead, the model finds the best values for each kernel's hyperparameters separately during the learning process. This is another incorrect answer. The length scales are not averaged, they are learned independently during model training. The linear kernel doesn't even have a length scale in the same way the RBF does. The radial basis function, RBF, kernel is my go-to for modeling smooth, curvy relationships. It has a length scale parameter that affects how wiggly or smooth the function is. I use the linear kernel to model simple, straight-line relationships within my data. This is the result of adding the RBF and linear kernels. It's the best of both worlds. This combined kernel gives me the flexibility to model both smooth curves and linear trends. I'm using Gaussian process regression, a powerful machine learning technique. I'm combining two types of kernels: the radial basis function, RBF, kernel and the linear kernel. Think of kernels as the building blocks that shape how my model learns patterns in data. This combination aims to capture both smooth, nonlinear relationships, RBF, and linear trends, linear kernel. This question tests my understanding of how combining kernels affects the overall model and its properties. I will evaluate each statement based on my understanding of RBF and linear kernels and how they work together. This statement is correct because I'm adding the kernels. The resulting model inherits characteristics from both. I will get the smoothness from the RBF kernel, allowing the model to handle curved relationships in data. At the same time, the linear kernel contributes to modeling linear trends. It's a powerful combination. This statement is incorrect. I shouldn't simply average length scales. The length scale of an RBF kernel controls the smoothness of the function and it is not directly combined like that when summing kernels. The overall hyperparameters are learned and optimized by the machine learning algorithm independently. Nope, this is incorrect. The hyperparameters aren't directly added together. Instead, the model learns optimal values for each kernel's hyperparameters separately during the training phase. Think of it as a more sophisticated process of optimization. This is false. While often a combined kernel improves the model, it's not a guaranteed win. The best performing kernel depends entirely on the specific dataset. Some datasets might favor a purely linear model, while others might benefit more from the flexibility of a combined kernel. I'm focusing on the radial basis function kernel, a key player in Gaussian process regression. It's all about modeling smooth, curvy relationships in your data. Think of it as a flexible curve fitting tool. This is a crucial hyperparameter in the RBF kernel. It controls how far the influence of a single data point extends to its neighbors. A smaller length scale means more wiggly curves. A larger length scale means smoother, broader curves. It's like adjusting the zoom on a microscope. Here, we're dealing with the straightforward linear kernel. This kernel simply models relationships as straight lines. It doesn't have the flexibility of the RBF kernel's curves and therefore doesn't need a length scale parameter. Think of it as drawing the trend line through your data points. This plus sign symbolizes adding the RBF and linear kernels together. In Gaussian process regression, adding kernels means combining their effects. The resulting model will capture both linear trends and smooth nonlinear patterns simultaneously. It's a powerful combination. This is the superstar of our discussion, the kernel that arises from combining the RBF and linear kernels. It inherits the strengths of both, allowing for modeling data with both linear and smooth, nonlinear components. It's like having the best of both worlds. The combined kernel will be able to model smooth curves from the RBF kernel and linear trends from the linear kernel in the data. This flexibility makes it adaptable to a wider range of data patterns.